There is an experiment so simple a student can perform it in a darkened room with a laser pointer and a piece of cardboard. Yet this same experiment has tormented physicists for over 2 centuries, challenged our most fundamental assumptions about reality, and remains, in the words of Richard Feynman, the central mystery of quantum mechanics. It's called the double-slit experiment, and what it reveals is so profoundly strange that even now, after countless replications with photons, electrons, atoms, and even molecules containing 2,000 atoms, we still cannot fully explain what it means. The setup is deceptively straightforward. You shine light through 2 narrow parallel slits onto a screen behind them. What appears on that screen should tell you once and for all whether light is made of particles or waves. Particles would create 2 bright strips, one behind each slit, like bullets fired through narrow openings. Waves would spread out, overlap, and interfere with each other, creating alternating bands of light and darkness, an interference pattern that only waves can produce. When Thomas Young first performed this experiment in 1801, he saw the interference pattern. The debate, he thought, was settled. Light is a wave, but quantum mechanics doesn't settle debates. It deepens them. When you send light through those slits, 1 photon at a time, single particles of light arriving so infrequently that only one exists in the apparatus at any moment, the interference pattern still appears, gradually, photon by photon, as if each individual particle somehow travels through both slits simultaneously, interferes with itself, and only then decides where to land. And, stranger still, the moment you try to observe which slit the photon actually goes through, the interference pattern vanishes instantly. The photon, as if aware it's being watched, stops behaving like a wave and starts behaving like a particle. It passes through one slit or the other, not both. The act of observation doesn't just reveal reality, it changes it. This is wave-particle duality, and it doesn't just apply to light, it applies to electrons, to atoms, to molecules, to matter itself. At the quantum scale, nothing has a definite nature until you measure it, and the choice of what to measure determines what kind of reality appears. For over 200 years, scientists have asked the same question in different forms, using increasingly sophisticated equipment and increasingly careful logic. What is actually happening here? And the answer quantum mechanics gives us is not comforting, it's not intuitive, it's not what anyone expected, but it is, as far as we can tell, true. In the 17th century, Isaac Newton proclaimed that light consists of a stream of particles, corpuscles he called them, traveling in straight lines and bouncing off surfaces like tiny billiard balls. His mathematical descriptions of optics worked beautifully. His reputation as the preeminent physicist of his era was unassailable. For over a century, the corpuscular theory of light dominated, but not everyone agreed. Christian Huygens, a Dutch physicist and contemporary of Newton, proposed in 1678 that light was a wave rippling through an invisible medium the way sound ripples through air. His wave theory could explain phenomena like diffraction and the bending of light around obstacles. But Newton's prestige carried the day, and Huygens's ideas were largely set aside. By the end of the 18th century, the particle theory seemed secure. Then, Thomas Young, an English physician and physicist, decided to test it. Young's experiment was based on a simple premise. If light were truly wave-like, it should behave the way ripples on a pond behave. When 2 waves meet, they either reinforce each other, if their peaks align, or cancel each other out, if a peak meets a trough. This phenomenon is called interference, and it is characteristic of waves. Young directed a beam of light at an opaque screen containing 2 thin parallel slits. On the other side, he placed a detector. If light were made of particles, he reasoned, you would see 2 bright strips on the detector, one directly behind each slit. If light were a wave, the wave fronts emerging from the 2 slits would overlap and interfere, creating a pattern of alternating bright and dark bands. What Young observed was unmistakable, a series of bright and dark fringes spreading across the screen. Regions where the waves from both slits arrived in phase reinforced each other, producing bright bands. Regions where they arrived out of phase canceled each other, producing darkness. It was interference. Light, Young concluded, is a wave. He presented his findings to the Royal Society in 1801 in a paper titled On the Theory of Light and Colors. The response was not enthusiastic. Critics, unwilling to accept that Isaac Newton could have been wrong, attacked Young's conclusions. In response to one such critic, Young wrote, "Much as I venerate the name of Newton, I am not therefore obliged to believe that he was infallible." Over the following decades, the wave theory of light gained acceptance. By the mid-19th century, James Clerk Maxwell had unified electricity, magnetism, and light into a single elegant framework of electromagnetic waves. The question seemed settled. Then, in 1905, Albert Einstein explained the photoelectric effect by proposing that light is not a continuous wave, but a stream of discrete particles, quanta of energy, later called photons. Each photon carries energy proportional to its frequency, and when it strikes a metal surface, it can eject an electron in a single, instantaneous collision. No wave theory could explain this. Light, Einstein said, is made of particles after all, so which is it? Wave or particle? Quantum mechanics answers both and neither, depending on how you look. In 1924, a French physicist named Louis de Broglie proposed something even stranger. If light, long thought to be purely a wave, could behave as particles, perhaps matter, electrons, atoms, everything made of particles, could behave as waves. He suggested that any particle with momentum has an associated wavelength, given by Planck's constant divided by the particle's momentum. The wavelength is extraordinarily short for macroscopic objects. A person running has a de Broglie wavelength far smaller than a proton. But for subatomic particles like electrons, the wave nature should be observable. Within 3 years, the hypothesis was confirmed. In 1927, at Bell Laboratories, Clinton Davison and Lester Germer fired a beam of electrons at a crystalline nickel target. The electrons scattered in a diffraction pattern identical to what X-rays, electromagnetic waves, produce when bounced off crystal lattices. Electrons were interfering with each other. They were behaving as waves. Simultaneously and independently, George Paget Thomson at the University of Aberdeen fired electrons through thin metal films and observed the same effect. Davison and Thomson shared the Nobel Prize in Physics in 1937. De Broglie had already won his in 1929. Matter, it turned out, has wave properties, not metaphorically, physically, observably, measurably. The double-slit experiment, originally performed with light, could now be performed with electrons, and when it was, the results were even more disturbing. In 1961, Klaus Jonsson at the University of Tübingen performed the double-slit experiment with a coherent beam of electrons. The interference pattern appeared, just as it did with light. Electrons, like photons, were somehow passing through both slits and interfering with themselves. But the truly definitive experiment came in 1974, when 3 Italian physicists, Pier Giorgio Merli, Gianfranco Misiroli, and Giulio Pozzi, performed the double-slit experiment with single electrons. They reduced the electron source to such low intensity that only one electron existed in the apparatus at any given time. There was no possibility of electrons interfering with each other. Each electron was alone. And yet, one by one, as the electrons struck the detector screen, the interference pattern slowly emerged. Each electron seemed to pass through both slits simultaneously, interfere with itself, and contribute to the overall pattern. In 2002, readers of Physics World voted this experiment the most beautiful experiment in physics of all time. In 1989, Akira Tonomura and his team at Hitachi refined the experiment further using even weaker electron beams and capturing the gradual buildup of the interference fringes in real time. The result was undeniable. A single electron traveling alone through the apparatus behaves as a wave. It does not have a definite path. It exists in a superposition of states passing through both slits at once until it reaches the detector and collapses into a single point. But here's where it gets truly strange. If you place a detector at one of the slits to observe which path the electron takes, the interference pattern disappears completely. The electron, now observed, behaves like a classical particle. It goes through one slit or the other, not both. The fringes vanish. You see two bright strips on the screen, exactly what you'd expect from particles, not waves. Turn off the detector and the interference pattern returns. The act of measurement changes the outcome, not because the measurement physically disturbs the electron in some crude mechanical way, but because obtaining information about the electron's path, which path information, as physicists call it, fundamentally alters the quantum state. This is not a flaw in our instruments. This is not a limitation of our experimental technique. This is how quantum mechanics works. Niels Bohr developed the complementarity principle to explain this. Wave and particle, he said, are complementary descriptions of quantum reality. You can design an experiment to reveal wave properties, or you can design one to reveal particle properties. But you cannot observe both simultaneously. The two aspects are mutually exclusive. Which one you see depends on the type of measurement you choose to make. In 1927, at the Fifth Solvay Conference, Albert Einstein challenged Bohr with a thought experiment. He proposed that when a photon passes through a slit, it should exert a tiny force on that slit, like a bird rustling a leaf as it flies by, as he put it. If you could measure that force, you would know which slit the photon went through. And yet, Einstein argued, the interference pattern should still appear. You would catch light exhibiting both its wave and particle nature at the same time. Bohr responded by invoking the uncertainty principle, formulated by Werner Heisenberg that same year. To measure the recoil of the slit with enough precision to determine which path the photon took, Bohr showed you would have to allow the slit itself to move. That movement would introduce enough uncertainty into the photon's momentum to wash out the interference pattern. The duality, Bohr demonstrated, is protected by the very structure of quantum mechanics. You cannot have both. Einstein was wrong. Bohr was right. And nearly a century later, in July 2025, physicists at MIT confirmed it with extraordinary precision. Wolfgang Ketterle, a Nobel laureate and professor of physics at MIT, led a team that performed an idealized version of the double-slit experiment using individual atoms as slits and single photons as the particles being detected. They used weak beams of light, ensuring that each atom scattered at most one photon. By preparing the atoms in different quantum states, they controlled how much which path information the atoms could acquire. The results were exactly as quantum mechanics predicted. The more information the atoms obtained about the photon's path, the more the photon's particle nature was probed, the lower the visibility of the interference pattern became. When the information was maximized, the fringes disappeared entirely. When the information was erased, the fringes returned. Einstein and Bohr would have never thought that this is possible, Ketterle said, to perform such an experiment with single atoms and single photons. The experiment confirmed at the atomic level what decades of theory and experimentation had already established. Wave-particle duality is real, complementarity holds, and the act of observation determines which aspect of reality you observe. But it also deepens the mystery, because it forces us to ask, what is the photon doing when we're not looking? According to quantum mechanics, the photon doesn't have a definite path until it's measured. It exists in a superposition of all possible paths. through both slits, neither slit, around the apparatus entirely, until the moment of detection collapses that superposition into a single outcome. The wave function, a mathematical description of all possible states, evolves deterministically according to the Schrödinger equation. But when a measurement occurs, the wave function collapses, and one specific result appears. This is the measurement problem, one of the deepest unsolved questions in quantum mechanics. What counts as a measurement? What causes the collapse? Why does observation change the state of the system? There are interpretations, many of them. The Copenhagen interpretation, developed by Bohr and Heisenberg, says quantum systems don't have definite properties until measured. The measurement process itself creates the reality we observe. The many worlds interpretation proposed by Hugh Everett says the wave function never collapses. Every possible outcome occurs, but in separate branching universes. When you observe which slit the photon went through, the universe splits. In one branch, it went through the left slit. In another, the right. You experience only one branch, but all of them are equally real. The pilot wave theory, originally formulated by Louis de Broglie and later refined by David Bohm, says particles always have definite positions and velocities, guided by a real physical wave that follows the Schrödinger equation. The particle goes through one slit, but the wave goes through both, guiding the particle's motion and creating the interference pattern. The relational interpretation proposed by Carlo Rovelli says quantum properties are not absolute but relational. They exist only relative to an observer. The photon doesn't have a path in isolation. It has a path relative to the detector that measures it. No experiment has yet definitively distinguished between these interpretations. They all make the same predictions for observable outcomes. The choice between them is, for now, a matter of philosophy, not physics. But the experiments continue, and they continue to confirm the same unsettling truth. The double-slit experiment has now been performed with photons, electrons, neutrons, atoms, and molecules. In 2001, researchers observed interference with Buckminster fullerene, soccer ball-shaped molecules made of 60 carbon atoms. In 2011, they used molecules containing 430 atoms. In 2019, the record was pushed to molecules of over 2,000 atoms with a total mass of 25,000 daltons. These are not subatomic particles. These are complex molecular structures verging on the macroscopic, and yet they still exhibit wave-particle duality. They still interfere with themselves. They still behave as if they occupy multiple places at once until observed. How far can this go? Is there a boundary where quantum behavior gives way to classical reality, where superposition collapses not because of measurement, but because of sheer size or complexity? These questions are at the frontier of research into decoherence and the quantum to classical transition. In 2023, researchers at Imperial College London performed a variation of the double-slit experiment not in space, but in time. They created materials whose optical properties could be toggled on and off within fractions of a second, effectively opening and closing slits in time rather than space. When light passed through these temporal slits, it produced interference, not as spatial fringes, but as shifts in color, frequency interference rather than spatial interference. The experiment, published in Nature Physics, opened an entirely new domain of quantum optics. The double-slit experiment also has profound practical applications. The wave nature of electrons is what makes electron microscopes possible. Because electron wavelengths can be up to 100,000 times shorter than visible light, electron microscopes achieve resolutions far beyond optical microscopes, revealing structures as small as 50 picometers, half an angstrom, and magnifications exceeding 10 million times. Modern biology, materials science, and nanotechnology depend on this technology, which exists only because matter behaves as waves. Neutron diffraction, based on the same principle, is used to determine the atomic structure of crystals and biological molecules. The de Broglie wavelength of thermal neutrons matches the spacing between atoms in solids, allowing researchers to probe structures that X-rays cannot reveal. And quantum computing, still in its infancy, exploits the superposition of quantum states, the very phenomenon demonstrated by the double-slit experiment, to perform calculations that classical computers cannot. A quantum bit exists in a superposition of 0 and 1 simultaneously, just as a photon passes through both slits simultaneously. It's only upon measurement that the state collapses into a definite answer. But perhaps more important than any application is what the double-slit experiment reveals about the nature of reality itself. For centuries, science operated under the assumption that the universe exists independently of observation. A tree falling in the forest makes a sound, whether or not anyone is there to hear it. The moon is there whether or not you look at it. Physical objects have definite properties: position, velocity, mass, and our job as scientists is to measure those properties as accurately as possible. Quantum mechanics shatters that assumption. At the quantum scale, properties do not exist independently of measurement. A photon does not have a definite position until you measure its position. It does not have a definite momentum until you measure its momentum. And because of the Heisenberg uncertainty principle, you cannot measure both with arbitrary precision simultaneously. The more precisely you know one, the less you can know about the other. This is not a statement about our ignorance. It is a statement about reality. The photon does not secretly have both properties hidden from view. It genuinely does not possess both properties at the same time. The universe at its foundation is indeterminate, probabilistic, and fundamentally interconnected with the act of observation. Richard Feynman, one of the architects of quantum electrodynamics, was fond of saying that all of quantum mechanics can be understood by carefully thinking through the implications of the double-slit experiment. He also said that nobody truly understands quantum mechanics. Both statements remain true. The double-slit experiment is over 2 centuries old. It has been refined, repeated, and extended in countless variations. It has been performed with particles ranging from photons to molecules, thousands of atoms large. It has been tested under conditions Einstein and Bohr could never have imagined. Every time, the results are the same. Wave-particle duality is real. Complementarity holds. Observation changes the outcome. And yet, we still don't have a complete answer to the simplest question: why? Why does the act of observing something change what it does? Why does obtaining information about a particle's path destroy the interference pattern? Why can't a photon be both a wave and a particle at the same time? Niels Bohr's answer was complementarity. The wave and particle descriptions are 2 sides of the same reality, revealed by different kinds of measurements. We cannot see both at once, not because of a limitation in our tools, but because the universe itself does not allow it. Nature, at the quantum level, is contextual. What you observe depends on how you look. But that raises another question, deeper and more unsettling. If reality depends on observation, and if particles exist in superposition until measured, what counts as an observation? Does it require a conscious observer, or is any interaction with a measuring device enough? And if measurement collapses the wavefunction, what determines when and how that collapse occurs? These are the questions that lead into the uncertainty principle, the topic that will occupy the next chapter of this story. Because the double-slit experiment doesn't just demonstrate wave-particle duality, it demonstrates that there are fundamental limits to what we can know, limits not imposed by our instruments or our intelligence, but by the structure of reality itself. The universe, it turns out, does not allow us to have complete information. And the reason is woven into the mathematics of quantum mechanics, discovered by a young German physicist in 1927, the same year Bohr and Einstein debated the meaning of the double-slit experiment. His name was Werner Heisenberg, and what he discovered would change our understanding of knowledge, measurement, and reality as profoundly as the double-slit experiment changed our understanding of matter and light. Because if the double-slit experiment taught us that observation changes reality, the uncertainty principle will teach us why. And the answer is even stranger than the question.